Hello everybody, today we'll be doing clone graph. Here we are given a reference node that is connected to a undirected graph and return a deep copy of the graph. So let's take a look at the first example we're doing. And we have adjacencies from every single node. So we have a node, let's check this out, let's see how it works. So basically what happens is that we're creating this node, like 1, with a that's connected to nodes 2 and 4. And then 2 will be connected to 1 and 3. And 3 will be connected to 2 and 4 again. And 4 will be connected to 1 and 3. This creates a box for us, like so. And how do you connect these graphs together? It's by creating a graph. We're creating a deep copy of the graph, and we cannot return the same copy of the same graph. So if we try to return the graph, this will not work for us. So return node. This is exactly the same, but as you can see here in this message, we cannot do that because it's not a copy, it's a reference to the original node given by the hash code. So if we use this function called deep copy, this will produce a deep copy of this node, and we will be able to return the right answer. Of course, this is submittable, but this code that we're submitting is based on the library, and it's pretty quick, isn't it? I guess it's worked very well this time, and I don't think we can produce something as quick. I don't know what they did. They tuned it with maybe using C++ behind the scenes, but it is much faster than implementing it yourself, and it's probably tested better as well. So, but what we're doing here is learning how to do this deep copy on our own and not using someone else's library. So let's see how it works. I think there are some edge cases that we need to take care of. Some edge cases might be that there are like infinite cycles where it points back to itself. So we do need to handle that with a visited. So we need to make a note of that. So in our plans, just say visited handle. Please handle that later. I don't know how to handle it yet in our plans, but it's something that we need to think about. So let's, is it possible to point back to itself? So let's say 1. That's a good question. And the answer is no. It says down here that there are no repeated edges and there is no self loop. And the graph is connected to all nodes that start from the beginning node, so we don't need to access other nodes. And it doesn't look like it wants us to access other nodes either because we're only returning a single node. The questions I would ask is that if this is the case, what happens if we have an empty item? Well, that just means that there are no connected nodes. And if there is also the other input where there is no node in the graph, and we just have to return none. So return none on no node. So if we try to input a node into our, like there's no node there, we have to handle the case, what will happen? So those are 2 things we do need to handle. So these are the input cases, okay? So this is going to be, the output will be return 1, node of 1, with nothing attached. And this is going to return a none. Okay, so we need to make sure that's the case when we return this code. So the time and space complexity, as we all know, is going to be O of n squared for these types of problems, because, well, what happens is that we have to visit a single node and all of its neighbors, and all of its neighbors can be connected to all of its other neighbors. So we have a maximum of like 1, if this is, connected as well. We would have 1 connected to 3 items, 2 connected to 3 items, 3 connected to 3 items, and 4 connected to 3 items. That's n times n minus 1. Which is basically n squared. For space, we also need to do the same because we're creating the same item, and if the item is going to cost us n squared, it's we're going to have to produce a brand new item that's n squared as well. So that's the time and space complexity. Our match is going to be a recursion. We can do this iteratively as well, but I think the recursive way of doing it is more, I guess, like in line. This algorithm matches the data structure better. So recursion. So how are we gonna do this recursion? First things first, we need a visited item, like to tell us that we have been there. Visited nodes. So once we have visited nodes, then we can visit all the nodes, and if we see it again, we can send it back to that particular location to get the node. So then we also need to recursively create nodes and connections. And that's all. And we need to handle visited, and we need to set none. So let's start implementing. So first things first, let's create that visited set, because that's very important. Visited, and what we're gonna say in our visited is gonna default to dict, where we hold nodes. The reason why we hold nodes is because, well, we want to say, oh, we have visited these nodes, and we want to save where they are at, and we can access them later. We can also say that we don't want to visit again and end up in an infinite loop where we keep going in a cycle, right? So let's show what happens if we do not have visited a node a little bit later after we done the visited. So we're going to create a DFS call to our node. And what this happens here is that we're going to send back a node where other nodes can point to. So what happens if we don't have a node? Do we call anything? We can say if not node, like if there's no node, return none, please. Okay, that's great. Elif like node is in visited. Oh, that's not right. This is on this line. Is in visited. Then we're gonna set our we're gonna return the visited at this node, which we're gonna store our old nodes. To new nodes. So basically. So now else. There's also a reason why we named this visited rather than old node to new node, is because we want to suggest that we have it's this idea of like notation, which allows the next reader to read the code and think very easily. Oh, this is what he's doing here. He's cloning a graph. He's creating a visited, basically dictionary, which will hold the old nodes and point to the new nodes. And if he's visited that node before, then he's not going to visit it again and just return the new node. That's the reason why it's called visited. It just sparks an idea about what's happening very quickly. And this using old terminology helps, common terminology helps other readers, maybe yourself in the future, to be able to read the code better. And now, now that we've handled all the edge cases, let's get to the recursive creating. So deep copy is equal to node at this particular node dot value. So we've created the value. And now we need to go for all of its neighbors for neighbor in node.neighbors. So for each neighbor, we're going to create a deep copy of it. So .neighbors.append a DFS call to our neighbor. So with that, we have basically created all we needed to create in our DFS call, and we can return our deep copy. So with that, I think we can just return our DFS call of our node. Yeah. Let's see if it works, and let's see what adjustments we need to make. Okay, so first item cannot be none. Must be callable. There seems to be an issue here. This does not work. Let's try that instead. This line of code does not work. Okay, what's the next? I think there's a problem. Okay, so we have an issue. And oh, we forgot to add the item into our visited set. So I think this makes it a lot easier. So we had an infinite loop because we forgot to add the item to our visited. So visited node is going to be equal to our current node, our deep copy. So now let's run the code, and it should work this time. All right, perfect. It's been accepted. Let's run through all our edge cases. Edge cases, these edge cases are included into our, as you can see, and let's submit. So with this, we have completed the problem. We have done our review, and we're going to do our evaluation. As evaluated earlier, what we have is a time and space of O of n, so squared, as seen here in our visited default dictionary, where we recursively create these items for each neighbor. So yeah, should I go into that with a little bit more detail? Maybe. Okay, let's go into it with more detail. So as you can see, we start with the first node. We go in and make sure it's not in the not a node and not in visited. Then we do a deep copy, and from this node, we visit all of its neighbors. So suppose we had 3 neighbors, right? So we're going to have to go through each neighbor and create all of its nodes as well, and go through a deep copy. So with that, we created all of its copies, and then we go through all of its neighbors and all of its neighbors, so it's n squared. We also, by creating this copy that has to go through n squared items, we create a deep copy that is n squared node, basically a number of nodes with all of its connections, which is n squared, n times n minus 1. So that's what we're doing here for evaluation again. And with that, we have completed the problem in pretty quick time, and we are good to go. And let's get to the next one. If you have better code or code that you would like to share, help us all learn together, please share it below, and let's learn at how this is how we can make better code. And so I think this one line would separate these would look better, and I think this is looking pretty okay. You know, let us know what can be better, and yeah, I'll see you in the next one. Like and subscribe, right?